There are only two people in the class. We are going to have a pop quiz which will count for 1% of the attendance. I'm just making sure that this is documented. Samyak, NC, just take a sheet of paper and you solve this problem. You get 10 minutes to do this. Okay?
Okay.
So consider the deformation defined by x1 equal to x3 1. Sit down. 10 minutes to solve this problem. 1% pop quiz. Get a sheet of paper from your notebook and start working on this. X3 minus x1 minus 2x2. X2 is equal to square root of 2 times x1 minus 2x2, and x3 is equal to x3 plus x1 plus 2x2. Part 1, compute the deformation tensor or deformation gradient f, which is defined as partial x over partial uppercase x, and compute J, which is the determinant of f, the Jacobian. So you get time is 5:33. You have until 5:43 to do these two problems. Pop quiz, 1%. 5:43 p.m. 1% do on a sheet of paper. 10 minutes pop quiz. Compute the deformation gradient and compute the Jacobian for this deformation. Go.
Can we use anything?
You can look up your notes or your textbook, but only 10 minutes. I have to move on with the lecture. Hopefully people will show up on time. I know today
This is for that, yeah.
take a sheet of paper, put your name and give it to me. Can refer to your notes or book textbook if you want. Since the spirit is getting you to show up, just doing one example, f11 would be partial x1 over partial x1, which is in this case -1. f12 would be partial x1 over partial uppercase x2, which in this case would be -2. So you have to take how this came about is derivative with respect to x1 of whatever is x1 in terms of the uppercase material coordinates, x3 minus x1 minus 2x2. Of course, derivative of x2 with respect to x1 or x3 with respect to x1 is 0, which leaves you with -1. For those who are like not sure. So compute the 9 components and the determinant of the matrix, you're done. Done? Yeah. Thank you. Also posted the YouTube videos. So we have a quiz going on until 5:43. You have 3 minutes to do this. I can't give you extra time because you weren't here on time. But in 3 minutes, whatever you can do, please do. You can just take a sheet from your notebook and do it. But I'll stop at 5:40. We have a quiz going on until 5:43. Whatever you can do in 2 minutes, please try. One minute more.
Should I email you?
Yeah, email it to me. Like take a picture and email it.
Okay.
All right. Last 30 seconds or so, please wrap up. We have to move on to our regular lecture. Tell your friends that I plan to do this for every lecture and ask them to show up one time. All right, please wrap up. We need to move on. Thank you. I'll give three possible scores on this quiz: 1, 0, 0.5, and 1. If you got something right, 0.5. If you got both the questions right, 1. If you don't show up or nothing right, 0. The request from me is please show up on time, preferably be here like a few minutes before 5:30. Okay, so that I can get started. I really end up losing the first few minutes because people keep coming in and it's not useful for us. Okay. All right. So we were discussing the unit on kinematics of deformation. I know it was a while ago, feels like 10 days ago. So what I suggest is please review the YouTube recordings of the two lectures. I'm going to give you a quick summary and then now move on. Our second exam is planned for the week of April 7th. Most likely we'll have it on April 10th, which is a Thursday. And that exam will cover almost fully this unit on kinematics of deformation. Because this is the basics on which the further units are constructed. So you had an exam on unit 1, you will have an exam on unit 2, and then we'll cover the remaining part of the course through homeworks and those mini projects. Okay. So first announcement is April 10th, we are going to have exam 2. And then so in this unit on kinematics, I'm going to put this on the homework as well, but the programming assignment is to calculate different deformation measures if the deformation gradient f is specified. Specified. That is, the input to your program should be the 9 components of f, and the outputs all the quantities discussed in module 2, which is chapter 3 of protection. To give you an example, we started with what is deformation gradient, f, which is partial x over partial material x, or this is another way of writing a mixed order tensor, Fij equals partial xi over partial xj. I talked in length about material coordinates and spatial coordinates, which I won't repeat. Please go review the video lectures if you want. So, for example, J, which is the determinant of F, is a quantity that depends on F itself. So where does J appear? J appear in calculating the change in volume in the spatial coordinates for a small change in volume in the material coordinates. We saw this last lecture. We also saw length changes. Like for example, dx vector is f dot dx, or another way of writing this is dxi is fij dxj. So we might, if we want to calculate, for example, a change in length specified as dx, what would be the change in spatial coordinates? So calculating quantities like these. Area changes. N cap dA is equal to J F inverse transpose dot N dA naught. Or this is another way of writing Ni dA is equal to J F Ji times dNj dA naught. So what I'm asking you to construct as a program is something that will take in a matrix as input and write out all the calculations that involve f, starting with the most simplest, the determinant of f. It's, if you just don't think about it as a tensor question, all I'm asking you to do is a bunch of matrix operations, starting with determinant, inverse transpose, products, and so on. For those who just arrived, there was a quiz and you missed it. You missed 1% of your grade. So please show up on time. So this part of the summary is what we have seen so far in 2 lectures. Understanding what is spatial coordinates, what is material coordinates. So maybe I should write that here. Spatial x and material coordinates. Deformation gradient. And then various measures of deformation. It's going to be a long list. We have just seen 3 of those now, and we are going to continue seeing more. Okay. Any questions so far? No. Were you here? April 10th, it's going to be example. Same format, open book, open notes, covering chapter 2 or chapter 3. Sorry. All right. 3.4.4, put forward and pull back operations. So you can think of the deformation mapping. The deformation mapping which we saw in the first lecture on this topic, x is equal to p of x. That is, a given reference configuration changes shape or changes is deformed, and this p is the function that describes the deformation. And we also derived the deformation tensor as, you can write this as partial x over partial x as we wrote. So when we say push forward, we talk about push forward is a mapping that transforms a material coordinate representation into a spatial coordinate representation. What do I mean by that? You can write any function, or you can write any quantity, express any quantity, any function or quantity can be expressed in either coordinates. A transformation from x to x is called as push forward. For some reason, we call this the forward operation, and anything that goes in the other direction would naturally be pull back. So remember this. So remember this. Let's say x is phi of x comma time. That is a deformation that also involves time dependence. So this is an example of a push forward operation because it takes the position of the particle in material coordinates and projects it onto the spatial coordinate. Now you can consider a quantity just want to use the same notation. So if I consider a quantity, let's say I call this consider the velocity field v of x comma t. If I ask you to just interpret this quantity based on how I have written it, what would your interpretation be? This is the velocity felt or measured or computed at a point whose position is x. This is spatial coordinate system. So this, if I vary x over the domain or the region of interest, I'm going to get a mapping of the velocity v at different points, just talking about it spatially. That's why this is spatial representation. If I write this v as a function of x of t, what is the interpretation of this representation? Be louder.
The velocity of the particles of.
The velocities of the particle, which is defined by the vector x at a given time t. Now, you can go back and forth between these two representations because you know a relationship between spatial and material variable, That is the deformation mapping. That deformation mapping generally comes from the nature of the material, the physics of deformation and the loading and so on. In this unit, we are of course directly given this. We don't talk about how the loading takes place. We just assume it takes place. So you can write x is equal to the inverse mapping of x comma t. Can you do that? Right? So if I write this, I can write this expression as v not as a function of x, but as a function of p inverse of x comma t. T. Can I write it this way? I'm just representing wherever phi x appears in terms of phi inverse. Okay. So what is the relation between this spatial velocity and this material velocity? I can also take this spatial velocity and write v. What is x? X is p of x comma t comma t. Right? I can represent any quantity in terms of the other or go back and forth between the other, which is what we call push forward and pull back, mapping one function into another coordinate and the other way. Okay. So this v here, v of x comma t, you can write. So this x is what? Do you agree with me on this? We saw this earlier. The change in position is related to the change in length through the deformation gradient. You can write this, you can extend this further and write v of x comma t is f dot v of x comma t. So if I want so this operation here is the example of push forward. And if I write the other way, v of x comma t is f inverse dot v of x comma t. This is an example of a pullback operation. You don't have to worry too much about how will I remember this. The important thing is for you to understand that deformation gradient is sort of a central concept which relates every other higher level of understanding. So if you start with deformation gradient, it itself talks about change in length only with respect to the coordinates. Then now we have found a relation between velocities of particles in terms of the deformation gradient. So we'll then again do this for energy and we'll strain energy and so many other higher order quantities. Always this F is going to be central to everything. That is why I'm giving you an assignment where you compute all the quantities that depend on F. Okay. I recommend reading this section, which talks in some more detail about the concepts we kind of mentioned. All right. May erase this portion. Three point 4.5 polar decomposition here. All right, before we do some math, there's a basic concept that I want you to help me understand. I don't know if you've seen this in your earlier courses on material science. Any deformation. So suppose you have torsion, for example. What is torsion? You hold the two ends and apply two countertops, or hold one end and apply a torque, right? You can write torsion as pure rotation plus like a transverse loading. You can almost write, okay, another example. If you are doing shear along a plane, you can always express a deformation as the sum of a pure rotation and purely, pure rotation plus a deformation. That is, torsion is basically torsion plus loading along one of the directions. What about shear? How can you express shear as a rotation plus a load? So the concept we are going to see here at the end of this discussion, you should be able to answer the question. The polar decomposition theorem is, yeah, right here. Any tensor F with positive determinant of F greater than 0 can be uniquely expressed as F is equal to R RU and equal to VR. I'll tell you what this means. What is F? F is what type of a tensor is F? Is it based in the spatial coordinate or is it based in the material coordinate? Mixed. F is a mixed second order tensor. That's why we write Fij with one index in the spatial coordinate and one index in the material coordinate. We can write this equal to Rii multiplied by Uij and then Vij times Rjj. Yep, Rjj. That is, we are getting a mixed order tensor as the product of another mixed order tensor R, which we will call the rotation component. And this is, what kind of a tensor is this? Uij, both I and j being in the material coordinate. This is the second order tensor. In material coordinate. coordinates. Likewise, this is again a mixed order tensor, and Bij is second order spatial tensor because it's both in spatial coordinates. Okay, I'll get to the part where it represents something. So what is F? F represents deformation. It is computed as the derivative of the there is Fij, you know, is partial xi over partial xj. That's how we started with. We are decomposing F into two components, one of which is the rotation. R is denoting the rotation tensor, and Uij or Bij is the stretch tensor. Uij is the stretch tensor in material coordinates, and Vij is the stretch tensor in spatial coordinates. The physical interpretation of this splitting is I am writing any deformation as the product or the sequence of a rotation followed by a stretch, which could be tension or compression, or a stretch followed by a rotation. What I'm saying is the rotation of the coordinates, the rotation happens first, followed by a stretch in the material coordinates, or vice versa. The stretch happens first, followed by a rotation of the coordinates. So this allows us to get more meaning or more insight about the distribution, or sorry, about the deformation that we are actually handling. In reality, how would one go about deriving F? Suppose you're not doing modeling, suppose you're doing experimental work or measurements, you would map out first this deformation mapping. That is, you would first get X as a function of material X. By marking 2 points, you have their initial length, you know their initial position. By applying a load, a given load, which we won't talk about, but it's some kind of loading, you can measure what is the change in length as well as the change in position of the coordinates. So you would first get this from the deformation mapping, you would get the deformation tensor. That is sort of the straightforward part. How do you interpret this F? You try to understand this as a product of R and U or V and R. Let me give you a simple example. What happens, or what is the interpretation if RII is the unit tensor or RJJ is the unit tensor? What is the interpretation?
Stretch is having.
Pure stretch. If you have the rotation tensor being the unit tensor, meaning Fij is same as Uij multiplied by the rotation tensor and the other way, you are first understanding what? That your deformation involves only changes in length and no change in orientation. Are you able to connect with that? If R is 1 or unity, it means there are only changes in lengths along the 9 possible combinations, and there is no change in orientation. What kind of a deformation would have that characteristic? Would pure axial tension have that characteristic? Uniaxial tension. Could there be any change in orientation in uniaxial tension? The way to think about this, if you are struggling, I'll give you my way of thinking about this. I imagine a rod. I put a small square patch along the circumference. In my mind, that is like a strain gauge sensor. When I apply a purely axial load, do I expect the small patch to change in shape or only change in length? It might be stretched. It may be a square initially. The square may become a rectangle. But do I expect my square to become a rhombus or a parallelogram? So that would be a case where there is only length change without change in orientation. Suppose I put the square, so here is your curved surface you can put the square parallel to the z-axis. You can also rotate the square by 45 degrees or whatever and make it look like a little rhombus. And then you do the stretching. Would your rhombus in this case change shape? If the orientation of your element is changed, would the element change its shape or only change its dimensions? How do you distinguish between change in dimension and change in shape?
Change in shape, either one of them.
Yes, either one of them got changed. If both got scaled up in, so if two sides get scaled up or two sides get stretched, you still have the same shape which are defined by the same angles. But if you start having difference in angles, that means your shape is changing. Okay. So the first example I'm trying to give you is empirically, you can get F. Once you get F through the operations that we are going to see now, you can decompose it into a rotation tensor and a stretch tensor in either coordinates. Looking at the rotation tensor, if it is a unity tensor, it means no rotation, it's just pure stretch. What if your rotation tensor has three values non-zero along the diagonal, but those values are not one? What does that mean? So I have a cylinder, let's say. I take my axis 1, axis 2, and axis 3. 1, 2, 3. So if I take my axis 1, my cylinder is initially oriented along that axis, and I give it a 60-degree spin. So that my R11 component would be cos 60. And that's the only operation I do, which means remaining 8 terms of this rotation tensor will be 0. Okay. So if I take my cylinder and if I rotate this about the axis 1, that is here is axis 1, which means axis 2 is here, axis 3 is here. If I rotate it like this, I'm going to get R2, R12 and R13 to be non-zero values. So your R tensor is essentially telling you how the rotation is taking place. R11 means it's about 1. I'm sorry, it's along 1. R12, R13 essentially represent the respective orientations in which you can do the rotation. So the way to think about this, I would suggest, is to do the math first, look at your tensor, and then try to interpret the tensor. Okay. What is the difference between this tensor and this tensor? Uij and Bij. Material and spatial, right? So for simplicity, if we consider that rotation is just not there, it's just a unity tensor. This allows you to understand how much the length changes and how much the position changes. That's what F is for, but sometimes it's hard to deconvolute what is a pure rotation versus what is a change in length or deformation. That is the purpose of this whole decomposition theorem, to split the total deformation as a product of two separate operations which are easier to interpret. Okay. Now we have to learn the math behind how we do this. So whatever I said so far, if you go to page 83, if you look at the last paragraph starting with the word considering right polar decomposition, it sort of explains what I've been talking about to understand the separation of rotation from the total deformation. Okay. So how do you compute this? So imagine you are working on your second programming assignment. F is already given. The next quantity that you want to calculate is R, U, and V. The rotation tensor, the material stretch tensor material stretch tensor and spatial stretch tensor. So I'm going to write R, which is R I or RJJ, whatever you want to call it, is the rotation tensor, and U, which is UIJ, is the material stretch tensor, and V, which is VIJ spatial, is the spatial stretch tensor. So we define C, the quadratic form of F, which is defined as F transpose times F. Okay. F transpose times F is equal to U squared, which we can write U transpose times U. So since C is a quadratic form, C is in a quadratic form, C can be written as alpha equals 1 to 3, lambda alpha C, gamma alpha, gamma. We saw this before in the first unit on tensors, and this process is called spectral representation of a quadratic tensor. So if C is in a quadratic form, we can calculate the eigenvalues of C and its eigenvectors and use them to construct a basis. U would be the same basis vectors lambda alpha C square root gamma alpha C gamma alpha C. So at the start of this class, I gave a pop quiz question, right? So what did we do there? So that problem is actually problem 3.7 of the text. F is given. You're asked to calculate J, which is determinant of F. And now I'm going to add also compute U ij, V ij spatial, and R ii. So what would you do? You would first to get, actually, let's finish seeing what is V and R, and we'll do this numerical exam. Okay, so let's leave it hanging here. So I'm going to rewrite this here. F is equal to RU is also equal to PR. So we are going to write, we just saw how to get U. We are going to next see how to get R, and using that we are going to get, sorry, we are going to see how to get B, and using that we are going to see how to get F. Sorry, how to get R. All right. So then we now define another quadratic form B, which we will write as F times F transpose. F times F transpose, which we will write is equal to B squared. This is B times B transpose. Quick question for you. Is C a material tensor or a spatial tensor or a mixed order tensor? Why?
The U is a.
Use the material tensor, you sort of knew that going in, but if this part weren't given to you, you just know about F. You can still do this by going from the first principles. What is F? F is Fij. That's the orientation in which we write F. What is F transpose then? Fji. So if we were to calculate F transpose dot F transpose dot F, that would be Fji multiplied by, I'm going to write this F I hope you won't mind because it's just a name, just a dummy index, multiplied by F, which is F Ig. That way I know that this summation will eliminate the spatial variable, and I'll be left with something which is Cij. At the end of this course, I want you to be able to do these kind of simple things using tensors. You might encounter tensors in some other context not related to deformation, but you should be able to still work with it. That's what I'm hoping you would pick up from this course. Okay. All right. Doing the same. What is the index of B? What is F? Fij. And what is F transpose? Fjj, which would make this Bij. The reason I'm forcing these two to be the same is the dot product. That will give me a delta Ij, which will then eventually make them the delta Jj, and that's what I'm keeping. Okay, so if B is equal to F times F transpose, express B in terms of its in its spectral representation, lambda alpha B, gamma alpha B, gamma alpha B, and V is the square root of gamma alpha B, gamma. So now all it remains for us to do is that we have at least two formulas for U and V. We know F, we have to get R, which you can do either using the first relation or the second relation. Right? So you can write R is equal to F times U inverse. You can also do R is equal to V inverse dot F. I'm just taking the first relation, multiplying both sides by U inverse, second relation multiplying both sides by V inverse, but in the forward direction. So again 10 minutes. Take that question I gave you. Let's compute U, V, and R. Wait, I don't know if we can do this in 10 minutes because you need to figure out all the eigenvalues. But I'm sure that for problem 3.7 is in the second one. So you will need to go back, do the spectral representation 2 times, and from that get R, U, and V, and then R. Okay, the R you get, you should try to. I mean, it's basically for your interpretation. That is, if suppose R turns out to be a unit tensor, you know what it means. If R turns out to be a tensor which has only the one component to be non-zero and every other component to be zero, you know what it means. It's a way for you to visualize that deformation. Okay. So next lecture, there will be another pop quiz wherein I might ask you to compute one of these quantities. I will give you the steps until like f is given, maybe even the eigenvalues are given, and ask you to do the next step. Something like that might come up. So please show up on time. Okay. Example 3.5. Okay. Problem 86, sorry, page 86. Example 3.5. We are going to discuss the example. NC, are you there?
Yes, I'm here.
Okay. Can I erase this part? Yes. So there is also a proof to this polar decomposition theorem, which I didn't go through. For our purpose, it's not really important. I thought knowing how to compute is more important. Okay. So example 3, page 86, example 3.5. What does it say? It gives you the deformation mapping. Consider the deformation mapping given in example 3.1. The deformation gradients associated with these mappings are given in example 3.2. Calculate C and U. Okay, that's what is R. CU and R. Okay, all right. So uniform stretching. What is the deformation mapping for uniform stretching? X1 equal to alpha x1, x2 equal to alpha x2, alpha 1 x1, alpha 2 x2, x3 equals alpha 3 x3. What is the deformation mapping for this? F is equal to alpha 1, alpha 2, alpha 3, remaining are all zeros. Okay, and what is C? C is F transpose times F. Luckily for us, transpose is the same thing. So this is basically alpha 1 squared, alpha 2 squared, alpha 3 squared, and remaining are zeros. It is already in a diagonal form. So the eigenvalues are right here in front of us. Alpha 1 squared, alpha 2 squared, alpha 3 squared. So it's sort of in a already the eigen form. And can you tell me what are the eigenvectors for this tensor? Just by looking at it. 1 0 0 0 1 0 0 0. Because you have elements only along the diagonal. the basis in which it is written is already in the eigenform. So you have the same eigenvectors. All right, so then what is U? U would be alpha 1, alpha 2, alpha 3. The remaining are zeros. It turns out F and U are really the same. If you write F is equal to R times U, R dot U, and if F and U are the same, what does it tell you about R? It's R is just identity. R is just the identity tensor, which means U is, sorry, which means U is equal to F, or F is pure stretch. F is a pure stretch. That is, the deformation represented by F is a pure stretch, which is what we were told. This deformations come from the idea that you either lengthen or contract along the x1 direction, same along x2 direction, same along x3. There is no shear here. Let's do this for the case where there is an applied shear. That is, if we take the deformation, x1 is x1 plus gamma x2, and x2 is same as x2 and x3 is same as x3. Can we do the same exercise for this deformation, which is, you know, this deformation? This is shear, planar shear, right? Would you agree with me on that count? That this is just taking a unit cell and extending the length along the direction 1 by not just proportional to x, but also x1, but also proportional to the x2 direction. That's what makes this a shear force. Okay. What is the deformation tensor for this? 1, gamma, 0, 1, 1. What is the C, which is F transpose times F for this tensor? You have to multiply. What is F transpose first? F transpose is 1, 0, 0, gamma 0, sorry, gamma 1, 0, 0, 0, 1. What is F transpose F? 1. So you have to multiply first row with first column, first row with second column. That will be gamma 0, first row with third column. Yep. And then second row with first column, second row with first column, gamma. Second row with second column with gamma squared plus 1. Second row with third column. Second row with third column 0. Third row with first column 0, 0, 1. Yeah, this is correct. Now, we need to quickly figure out, of course, this is not directly true. What are the eigenvalues for this tensor? I can write 1 minus lambda times 1 minus lambda times gamma squared plus 1 minus lambda minus gamma squared equal to 0. I'm taking this element, multiplying with this determinant to get this calculus. Of course, the first unit we saw this with a lot of steps. I'm compressing a lot of it. Okay. So gamma equal to 1 is obviously one of the eigenvalues. That's easy. And can we simplify this? So we have 1 minus lambda times gamma squared plus 1 minus lambda whole squared minus gamma squared equal to 0. So this will be plus gamma squared minus gamma squared. So this will go away. So I have minus lambda gamma squared plus 1 minus lambda whole squared equal to 0. It's not pretty, but it's still solvable. Lambda squared minus 2 lambda minus gamma squared lambda plus 1 equal to 0. Or lambda squared minus lambda times gamma squared plus 2 plus 1 equal to 0. Please look at this and tell me if I made any mistake. So it says 4 plus gamma squared. I have only 2 plus gamma squared.
Minus lambda is a gamma squared minus lambda.
1 minus lambda squared. It should be minus 1 minus lambda times gamma squared plus 1 minus lambda the whole square minus gamma squared. Okay, I don't want to be drawn into this because I am prone to making such mistakes. We will eat up all our time. But the idea is you solve for the other two eigenvalues. You are already able to derive 3 eigenvectors for a given tensor, this tensor. So represent C in terms of its eigenvalues. All you have to do is take the square root of the eigenvalues to get the representation for U. C and U have the same basis vectors. Does that strike you? They have the same basis vectors. Once you derive the eigenvectors, you are like 90% done. Then all you have to do is take the square root of the eigenvalues to get U. Okay? All right. So section 3.4.6 continues to discuss the physical significance of these stretch vectors or stretch tensors. So section 3.4.6 deformation measures and their physical significance. So F is written as RU and as well as VR. So you can see here R multiplied by U and then V multiplied by R. For that reason, U is called the right stretch tensor and V is called the left stretch tensor, which to me is very confusing because I always get left and right mixed up. To me, this notation of calling it material and spatial makes more sense. It's expressed in terms of material coordinates. It's a material stretch tensor. That's it. Same thing about spatial stretch tensor. Okay. So when you read the book, when you see the term right and left, please connect it with the material and spatial. Okay. So let's consider dx. What is dx physically? It is the change in length of a particle represented by the vector x. Change in position vector, material position. When I consider dx dot dx, I can write this is equal to ds squared, or write ds is equal to square root of dx dot dx. What is this quantity? What is this quantity? How do you interpret it? If dx is change in position, what is square root of dx dot dx? Change in length. This is total change in length, and since you are doing a dot product, it is summed over all three directions. Okay, so ds is square root of dx dot dx, and if I consider square root of dx spatial dot dx, I can write this is ds. This would be total change in position or linear position. Can we do this a little bit in tensor notation? What is ds spatial squared? This is dx dot dx. What is x? Or what is dx? That is the deformation gradient dot change in position of the particle. Change in length, sorry, change in the spatial coordinate is related to the change in the length via the deformation gradient. So I can write this dxi is fij dxj. Can I? We've been doing that all day. Okay. So this is fij dxj, and this is fi dxi. Why? Why am I writing it twice, but writing it with different? I write this I and this as j. Why am I writing it as dx? Here I use I and here I use j. Sorry?
Change in position.
Okay, the one you're right, but one more part to that question is why am I using a common I but different material coordinates? So I can start with writing this as FII dxi. What, this is a vector or a tensor or a scalar? What kind of a quantity is this? You're already summing over I. The only non-repeating index is spatial I, which would make this a vector. So this is like writing EI dot F. You can call it whatever you want. FJ, FJJ, DXJ, EJ. The reason I use I here and J here is this quantity is a sum, it's not a single quantity. The fact that I repeats here means it is the short form for 3 terms, right? So you should in general use a different index here so that you get all the 9 products instead of only one product. And here I use I, EI cap, here I use J, EJ cap. Invariably, I'm going to end up with EI.EJ, which will get me a delta function. So this is eventually going to become FII DXI, Fij DXJ, which now is just a product of scalars, which I can write FII, Fij, DXI, DXJ. Okay, what is this quantity FII and Fij multiplied by DXI and DXJ? You recall what is C? C was F transpose times F, right? Making sure. Yeah, F transpose times F. That would be F II multiplied by F Ij. Okay. Now this quantity here is not the same as this quantity here. How did they write that? AI. Maybe we'll pick this up next time. There is one small step we need to do here. Start next time. Okay. So your homework, especially the programming assignment, what you should try to do is you can take example 3.7. Okay. Example 3.7. Consider that problem as an input to your code. You should start writing your MATLAB code or whatever language you use. Start computing, starting with F as input, compute J, and then compute C, U, compute B, B, and then go on to R. All of this should be done by your program. Everything is just a set of matrix operations. So you should be able to start doing it with MATLAB almost easily. Okay. So every lecture, when we complete a new quantity or finish discussing, you should go home and add that function into your program so that during the submission, you can just turn in that program with a list of outputs and you're done. 5% credit for that. Who gives 5% credit for matrix multiplication? I do. Okay, so start working on that along with your homework too. I think I've posted it. If not, I'll check again and post it. Thank you. And please